Let's begin Chapter 2 and take a look at Section 2.1, Basics of Functions and Their Graphs. Let's see what the objectives are. We need to be able to discuss the difference between a function and a relation, and if it's a function or a relation, we need to be able to determine the domain and the range. We also need to know whether a function or its graph represents Let's begin Chapter 2 by looking at Section 2.1, Basics of Functions and Their Graphs. Some of the objectives include discussing the difference between a function and a relation, and describing the domain and range of a function and a relation, knowing whether a graph or a set of ordered pairs represents a function, being able to plot some points to graph a function, and some other details that we will get to momentarily. Let's take a look at the content. A relation, well, it's called a relation because it is a relationship between two things. Take two sets of ordered pairs, say x comma y. The set of all first components, normally called x, are the domain of the function, and the second element of the ordered pairs, usually called the y, represent the range of that relation. For example, here's a set of ordered pairs, and the first component, 0, 10, 20, 30, and 40 represent collectively the domain of the function, and the second component here represents the range of that list of ordered pairs. Definition of a function. It's very specific. A function is not just a relationship between two things. It's a very specific relationship. It's a relationship in which the first element, usually called the input, goes to exactly one output value, and that would be a function. Each input goes to exactly one output. For example, to determine whether this list of ordered pairs represents a function or a relation, we look at each first component, the elements of the domain, and they map to only one element of the second component, the range, which means that here we have a function. For instance, if you were to interchange these ordered pairs and write this one as 5, 6, and write this one as 5, 8, now, the number 5 is double valued. It maps to both 6 as an output and 5 maps to 8 as an output. So 5 we say is double valued, 5 maps to 6, and 5 maps to 8. So that does not represent a function. In this case, it's simply a relationship between the input and the output. Let's go on to the next. How can you tell if an equation represents a function? Well, we'll take the relationship defined as an equation, and if we solve the equation for y, and then imagine putting a value of x in, how many values of y do we get out? If the answer is 1 and only 1, then we have a function. If it is more than 1, then it is called a relation. For an example, if x squared plus y squared is equal to 1, since we have y to the second power, when we attempt to isolate the y by itself, we eventually have to take the square root to get rid of the square. When you take the square root, you always get plus or minus. That means for each given value of x, once we compute the value of the square root, we get two answers for y, a positive and a negative value. That makes one value of x map to two different values of y, and that would not be a function. If you had, say, 2x plus 3y equals 10, now if we attempt to solve that equation for y. Since y is to the first power, we will not have to take a square root or a fourth root or a sixth root, so this will result in having one value of y for each value of x. So solving the equation for y very carefully, so 10 thirds minus 2 thirds x. Given one value for x, we simply take 2 thirds of that, and then 10 thirds minus that quantity gives us one and only one value of y, so that would in fact define y as a function of x. Function notation. This is extremely important and pervades all the mathematics, especially at the higher levels, and it's always a source of confusion. Function notation, when you write the ordered pair x comma f of x, this second component is always the function, and the first component here is always the variable. And given a value for x, we can compute the value of y by substituting that value of x into the function, and that is what we mean by evaluating the function. So let's take a look at an example. Here we have f of x equals x squared minus 2x plus 7. This is the same thing as writing y equals x squared minus 2x plus 7, but the function notation is there for a reason. When you say find f of negative 5, this means when the x value is negative 5, find the corresponding y value. And all of that is in this notation f of negative 5. Simply means to go to the function and replace each x by negative 5. So each of these x's here will take on the value of negative 5, and when we substitute that in and do out the arithmetic carefully, we get the value of 42. When we conclude and say that f of negative 5 equals 42, this means exactly the same thing as the ordered pair. When x is negative 5, the y value is 42. And that does define a point in the Cartesian coordinate system. Okay, simply make a graph of a function. We simply find a list of ordered pairs. We graph those ordered pairs on the x and y coordinate plane, and then we connect those with a smooth line or curve. For example, if we wish to graph the function 2x and 2x minus 3 in the same rectangular coordinate system, we can do so by selecting values of x. These are values in the domain, and then computing the corresponding y values. Those are elements in the range, and they will define ordered pairs for the function, and we will then graph them. So let's proceed on to do that work. So here we have value of x running from negative 2 using integers through positive 2. The function is f of x equals 2x. This is the doubling function, which simply means take the value of x, multiply it by 2, and you obtain the value of y. Y is always the same thing as f of x. So when x is negative 2, we simply double it. Each value of x we double, and we will then have a list of ordered pairs for the function 2x. Now we have another function that's different. It's 2x minus 3. So in this case, we define it by not saying f, but name it with g or h or k, a different value of a letter to indicate that it's a different function. So here we call it g. G is 2x minus 3. So we can substitute values of x in the g function. We can then double it and then subtract 3. A different way to think about it is the difference between the f function and the g function is the g function subtracts 3. So if you take these y values here and subtract 3 from each one, you will obtain the values for the g function. Or you can manually do the arithmetic. We plot each of these points as indicated here by the dots on both of the graphs, and then draw the nice smooth, in this case, line connecting those. We obtain the graph of both. Notice that these two lines are parallel, and the reason why they're parallel, meaning they keep the same distance apart, is because the slope of this line is 2, and the slope of this line is also 2, and slope is a measure of the amount of inclination to the horizontal, so they're both turned at the same amount. They're both the same steepness. The minus 3 simply means that you take the graph of the f function, and if you slide every y coordinate down by 3, you can obtain the graph of the g function. This is called a graph transformation. In particular, it's called a vertical translation. Okay. Vertical line test for functions. This is how to tell whether the graph of a function is a relation or a function. Since each x can only correspond to exactly one y value, that means on the graph, if you were to look at various values of x and draw a vertical line through all particular values of x, like this, if you can pass that vertical line through the curve at more than one place, it cannot be a function because, say, this value of x would correspond to this value of y, and that value of y, that would be double valued, and so would not represent a function. Whereas in this example here, any vertical line that is passed vertically through the graph will only intersect the graph at one spot, meaning that one x goes to only one y value, and so that does represent a function. So it literally is using the definition, but in a visual way applied to the graph. Let's look at an application problem here. Example 7. Use the graph to find f of 5. Remember that f of 5 means when your input is 5, find the output value. Okay? Well, here our inputs are measured to be the time after infection, the number of years after infection, and the y values represent the average T cell count per milliliter of blood. So we can also say that f of 5 means find the average T cell count given that the time after infection is 5 years. This would be the interpretation in context of f of 5. How do we do it? Since the variable is 5, we go to 5 on the horizontal axis and locate that. We go up to find the graph. There it is. And then horizontally across to find its corresponding functional value, which is 400. So f of 5 would then be 400. Here's a different question. For what value of x is f of x equal to 100? So this means if y is 1,000, then what is the corresponding value of x? So this is the reverse of what we were just doing. So what I'll do is I'll find the y value of 100 on the graph. Here are the y values here. 100 is approximately here. We'll go across to find the graph. Right there it is. Go vertically down to find the x value, and we get 9. So f of 9, when x is 9, the y value, f of 9, is equal to Let's take a look at how to identify the domain and range from a function's graph. The domain of a function is the set of all inputs from the graph, so this means the horizontal axis. It's another way of saying find the extent to which the graph extends to the left and to the right, whereas the range of a function from its graph is asking for the functional values of the y-coordinate. That is the amount the graph extends vertically from the low to the high. Best by example. Here's the graph of a function. Let's use the graph to identify the domain and the range. Okay, so the domain is how far this graph here extends horizontally from the left and the right. It's asking for essentially the left bound, which is here, to the right bound, which is here. So the value starts at -2. You can see the solid dot there, so -2 is included. And for all values of x all the way up to 1, including 1s, see the solid dot there, we have corresponding y-coordinate on the graph. So this notation means all values of x between -2 and 1, including, there's the equal sign, including -2 and including 1. A different way to write that here is with interval notation, and this is the most common notation used in higher level math. This indicates the left to the right, the leftmost value and the rightmost value. Including, which is solid dot on the graph, is including here equal to with the inequality, which means a closed bracket, squared bracket here. And also including 1 right here, the solid dot, also means the equal to and the inequality, also is a square bracket. So this is the interval for x from -2 to 1, meaning there is a y-coordinate on the graph for all x values between -2 and 1, including -2 and including 1. The range is how far the graph extends vertically. So we have a low value here, and we have a high value right here. The low value is on the x-axis, so that's where y is 0, and the high value of y right here is where y is equal to 3. And we have closed endpoints here, so that means from 0, including 0, up to and including 3. So all y values between 0 and 3, including 0 and including 3. So that would be the closed interval, square bracket, 0 to 3. All y's between 0 and 3, including 0 and 3, would represent the range. Let's take a look at example 9. This is similar. Use the graph of the function to identify its domain and its range. Okay, so again, domain is looking for the extent of the graph from the left to the right. But notice that there is an open circle here on the left. That means the value of -2 for x is not included, and the solid dot here means that it is. So we respond in the same way as before, using the inequality notation. All x's between -2 and 1, but the open circle means not including. And the way we write not including is to not have an equal sign there. The corresponding interval notation means that you have a parenthesis there and not a square bracket. That means not including that endpoint on the left at x equals -2. All the way to the right endpoint, which is included on the graph, you can see the solid dot. So that is the equal sign here in the inequality and the square bracket here in the interval notation. This is called a half-open interval, or you could say half-closed. Either way, it's not a fully open interval and it's not fully closed. And the range of the function, as done before, is the low y value to the high y value. That would be from here at -1 to here at 2. Look very carefully. This y value here at -1 is included. That's the solid dot. And the value of y equals 2 is not quite attainable. So that's the open circle. So again, the inequality notation is -1 to 2, including -1 equal sign, not including 2. And then not including 2 is a parenthesis and not a square bracket. So that's another half-opened, or if you wish, half-closed interval that represents the range of that particular function. Okay. Let's take a look at identifying intercepts by looking at graphs. This is best done by showing an example. Identify the x and y intercepts for this particular graph of f of x. Now, when you write f of x notation, that means the graph is a function, which means it does pass the vertical line test. You can see any vertical line drawn would only intersect the graph at most once. So this is indeed a function. The x-intercepts are where that graph passes through the horizontal axis. So where this graph passes through the axis is right here, and right here. There are 3 x-intercepts for this particular function. Now, because you're on the xy axis, every point is designated by an xy coordinate. So it is much more proper to write the x-intercept as a coordinate. Here it's -3. The y value is 0. Since you're not above or below the axis, the y value must be 0 there. That identifies that to be an x-intercept. Here's another x-intercept at -1. So again, the y value is 0, and the place where The graph crosses the x-axis is at -1, so -1, 0 is the proper way to record that intercept. And once again, here it crosses the x-axis at 2, so that's at 2, 0. The y-intercept is where the graph passes through the vertical axis. That occurs right here. And most would say the y-intercept is -6, but the proper way to write it is both using x and y coordinate. The x-coordinate is 0 since x measures the distance to the right and left of the y-axis. So at the y-intercept, the x must be 0, and the y value is then -6. So you can see that all x-intercepts are identifiable by having the y value of 0, and all y-intercepts are identifiable by having the x being 0. That, by the way, tells you how to proceed to find x and y intercepts from an equation of a function.